In this video, I'll talk about the SP mixing. I'm teaching inorganic chemistry this quarter. Many students got confused by SP mixing. This is normal. I think there are two reasons. Reason one, most textbooks simply mention that the SP mixing is much more significant in B2, C2, N2 than in O2 and F2 without adequate explanation. Reason two, students really have to study quantum chemistry or quantum mechanics before they can truly understand the SP mixing. So I'm going to try to explain this phenomena using quantum mechanics. Let's look at the molecular orbitals of O2. All right, so we have this MO diagram of O2, and then 1s, 1s, those are core electrons. Chemists do not care about core electrons. Valence electrons. Now we have 2 electrons in the 2s orbital on the left, 2 electrons on the right. They form sigma G and sigma U star. And we put 2 electrons here, first in the lower energy orbital, and then 2 electrons in the higher energy orbital. The bond order is 0 because you have 2 bonding electrons here, 2 anti-bonding electrons here. They cancel. Now p orbitals, we have 4 electrons in this, 3 p orbitals on the left, 4 electrons on the right. This 3 p orbitals and this 3 p orbitals overlap. They can form sigma G here. Again, this is head-to-head interaction. And then shoulder-to-shoulder interaction. 2 of them, because you have x direction and y direction, they are degenerate. Now pi star, and then sigma star. So again, this LCAO theory, linear combination of atomic orbital theory, tells us if we start from 6 AOs, we should end up with 6 MOs. All right, and then we put those 8 electrons into the lowest energy orbital first, 3 sigma G, and then 2 here, 2 here. We have 2 more left, 1 here, 1 here. The Hund's rule tells us these 2 should have the same spin. In quantum mechanics, you will learn that the 2 electrons with the same spin can better avoid each other. All right, that will reduce the repulsion between the 2 electrons, and then you have lower energy. So this electron configuration has lower energy than 1 alpha, 1 beta. All right. So this is O2. What about F2? Well, F2, you just put 1 more electron here, 1 more electron here, and then you put 1 more electron here, 1 more electron here. Done. That's F2. Really simple. Okay. F has 1 more electron than O. That's it. The bond order of O2 is 2. You have 6 bonding electrons here, 2 anti-bonding electrons here. So 6 minus 2 over 2, that's 2. Bond order is 2 for oxygen. The bond order of F2 is 1. Because of the spin of these 2 electrons, O2 is paramagnetic. So if you just Google liquid oxygen magnets or magnetic field, you will find, many videos in which an instructor pours liquid oxygen between the N pole and South pole, and the liquid oxygen will be attracted between the 2 poles. All right, because the liquid oxygen is magnetic. More specifically, we call that paramagnetic. It's different from ferromagnetic, but anyway, it's magnetic. All right, so get back to SP mixing. I want to say, in short, because the energy gap between this 2s and this 2p is so large that, you know, this 2s does not interact with 2pz here. There's no interaction between 2s and 2pz. So this orbital is purely formed from 2pz and 2pz in oxygen and the fluorine, approximately. And over here, this is just completely just from 2s and 2s, okay, in O2 and F2. In boron 2, carbon 2, and nitrogen 2, the energy difference between 2s and 2pz is so small. Okay, so there are two ways to look at the sp mixing. One is that this 2s and this 2p are mixed first. And then you have two mixed atomic orbitals. And they interact with these two mixed atomic orbitals from the combination of 2pz and 2s. And then they form the MOs with both S character, mostly S character here, but also a little bit P character. And over here also the same, you have mostly P character and a little bit S character. This kind of interaction will bump this 3 sigma G up and bump this 2 sigma G down. So this level will be here after the sp mixing. And this 3,6G will be here after mixing. Look, when I move this 3 sigma G here, this is above the 1 pi u orbitals. And that's why in B2C2 nitrogen 2, you have this 2 degenerate 1 pi u orbitals sitting below the 3 sigma G. Okay, again, this is because the gap between the 2s orbital and the 2pz orbital is so small in carbon 2, boron 2, and nitrogen 2. Okay, now let's talk about quantum mechanics. In quantum mechanics, two MOs with the same symmetry about the bonding axis. So along the bonding axis, if they have the same symmetry, they can interact with each other. For example, this 2 sigma G can interact with this 3 sigma G. Alright, so again, this is the bond. If you look at the bond axis and the rotation of this sigma G about the bonding axis is totally symmetrical. So again, this is bonding axis. If I rotate this sigma G orbital about this axis, 1 degree, 2 degrees, 2.5 degrees, you cannot tell the difference. And same here, same here. Okay, so these two have the same symmetry along the bonding axis, right? So they can mix. And if they mix, they can generate two new MOs. The two new MOs will have different energies from the two original MOs. Among the two new MOs, the higher energy one will lie above the two original MOs. All right. The new lower energy MO will lie below the original two MOs. All right. And the higher energy MO will resemble the shape of that. Will resemble the original higher energy MO, and the new lower energy MO will resemble the original lower energy MO. All right. So those are quantum mechanical phenomena. So in this case, in B2 or C2 or N2, the new higher energy MO lies much, much higher above the original 3 sigma G MO. So you shift this MO way up. It even lie above the 2 degenerate 1 pi u energy levels. All right. Mathematically, we can calculate quantitatively how the energy levels shift after mixing. So we're going to do that. We have this 2 sigma G orbital and 3 sigma G orbital. 2 sigma G is made of the 2s orbitals. 3 sigma g is made of the 2pz orbitals. So this 3 sigma g lies above 2 sigma g, okay? In boron 2C2, nitrogen 2, O2, and F2. So in all this homonuclear diatomic molecules. So I'm going to say this is my E2. The energy is E2. This energy is E3. Both E2 and E3 are negative, okay? E2 is more negative than E3. All right, so in quantum mechanics, we learn how to calculate the energies of the new MOs by solving this equation. This is a 2x2 determinant, so you need to learn some linear algebra as well. So we set this 2x2 determinant to be 0, and E2 is the energy level of the 2 sigma g orbital. E3 is the energy level of the 3 sigma g orbital. Both E2 and E3 are negative. E2 is more negative than E3. That means 2 sigma g lies below 3 sigma g. Now, what is R? R is the resonance energy between these two interacting MOs. R is typically between 5% to 10% of E2 or E3. All right? So you may say, what? Is it E2 or E3 or both? What if E2 and E3 are different? Okay, when E2 or E3 are quite different, there's not much interaction between the two MOs anyway. Don't worry about that. So usually when E2 and E3 are close to each other, we observe significant interaction between these two. We observe the energy shift of the new MOs. All right. So in that case, when E2 and E3 are close to each other, so it doesn't matter which one you use, and it's between 5% to 10%. However, if this MO and this MO have different symmetry about the bonding axis, then R is just absolutely 0. There's no interaction. R is also proportional to the overlap between the two interacting orbitals. So in this case, we are looking at this 2 sigma g and 3 sigma g. So R just tells us how much these two overlap. If they overlap significantly, R is big. If 2 sigma g and 3 sigma g overlap just by a little bit, then R is negligible. All right, get back to the mathematics. So really, you just need to know how to solve this. After we expand the 2x2 determinant, you get this. This is just a quadratic function of x, right? So solve it. We get this. This is the exact solution. So the two new energy levels will be this. It looks quite complicated, but over here, this is just the average of the energy levels of 2 sigma g and 3 sigma g. So this is the center, okay, between 2 sigma g and 3 sigma g. All right, so you find the center and then shift up and down. So this part is maybe too complicated. We'll simplify this part, okay? When E2 is equal to E3, well, this part is just 0, and then we take the square root of this. We get 2R. 2R over 2 is R. So really, X is just equal to E plus minus R. All right, so the two new MOs, one sitting above the original E, one sitting below the original E. The shift is R. So that's really simple. But that's not the case for this situation. All right, so we know 3 sigma G lies above 2 sigma G. This is because 2pz orbital has higher energy than 2s orbital. And this is made from 2pz orbitals. This is made from the 2s orbitals. So this is not the case. I'm just trying to tell you different cases. Now let's look at the different cases. Okay, different cases. Before we talk about different case in which E2 and E3 are quite different, let's look at this equation again. This equation also explains why the splitting between sigma and sigma star is usually larger than that between pi and pi star. So I want to show you the O2 MO diagram again. Alright, so this is O2 diagram. Alright, so 2pz and 2pz, they form sigma g and sigma u star. So look at the splitting here. This is really big. Now look at the interaction between 2px and 2px, 2py and 2py. Look at the splitting between pi and pi star. So this splitting between pi and pi star is smaller than the splitting between sigma g and sigma star. Alright, why is that? Well, this is the so-called head-to-head interaction. There's more overlap. Okay, more overlap here. Alright, and this is the so-called shoulder-to-shoulder interaction. Alright, typically shoulder-to-shoulder interaction causes less overlap than head-to-head interaction. Okay, head-to-head interaction is more significant than the shoulder-to-shoulder interaction. So when you have a stronger interaction, you have a larger R. And when you have a larger R, you have a larger splitting. Alright, so the R for the sigma G, sigma U star splitting is larger than the pi U to pi star splitting. So this is actually 2 times R for this interaction between 2pz and 2pz, head-to-head interaction. And this is 2 times R for the shoulder-to-shoulder interaction. Alright, so I somehow kind of sidetracked. Okay, now get back to the MOs, alright? The principle is the same. You can use the same principle to analyze the interaction between 2 AOs or the interaction between 2 MOs. So now let's get back to the interaction between the 2 MOs, between the 2 sigma G and 3 sigma G MOs. Okay, in this case, 3 sigma G lies above 2 sigma G. The energy is different. Alright, so we have something here. And then if they are quite different, we have this squared greater than 4r squared. Alright? And then I'm going to use a mathematical trick. The trick is I'm going to just add one more term to this. So you have this squared, this squared. I'm going to add one more term here. Why can I add this term? Well, again, if we can assume this okay, this let's see. I want to say the absolute value of E2 minus E3 is much greater than R here, but I didn't do that, so I'm just use squared. So I want to say because of this, I want to say this term is much smaller than this term and than this term. Alright, so this is much smaller than this and this. So this is my approximation. Over here, I arbitrarily included a third term in the square root. Okay, not arbitrarily. I designed this. Alright. My point is, over here, let's say this is $100. This is $10. And this is 1 cent. So you are looking at $100 plus $10. Alright, that's $110. Plus 1 cent. That's $110 and 1 cent. It's approximately equal to $110 here. Alright, so that's my justification. The reason I designed this third term is because now you are looking at actually this 3 terms. The sum of the 3 terms is actually this plus this squared. Alright, remember a plus b squared is a squared plus b squared plus 2ab. So this guy squared is here. This guy squared is here. And what about the cross term? The cross term is 2 times this times this. Okay, 2 times this, which happens to be 4r squared. So that's my trick to simplify this square root. Okay, so now I got this. The rest is simple algebra. We have a plus sign here, a minus sign here. We do the plus sign here. The result is this. So if you look at this, this is just E2 plus a correction. this correction is negative because E2 is smaller than E3. So this new MO has lower energy than E2. Now I'm going to use negative sign here. When you use the negative sign, we get the energy level, new energy level here, which is higher than the original E3. Again, this is because E2 is more negative than E3. So this term is actually positive. Now you get two new MOs. The lower energy MO, new MO, has even lower energy than the previous E2. The new higher energy MO has even higher energy than previous E3, and this is almost always true when two orbitals interact with each other. All right. Okay, so this is my conclusion. The new lower energy MO lies below the original lower energy MO. The new higher energy MO lies above the original higher energy MO. In B2, C2, and N2, the shift is so significant. Why? Because in B2, C2, N2, E2 and E3 are so close to each other. Look at the denominator here. This denominator is small, therefore the shift is large. When the shift is large enough, we can bump this 3 sigma G orbital to above the two degenerates 1 pi u energy levels. All right, but in O2 and F2, the energies of this 2 sigma G and 3 sigma G are so different, and this is fairly large. Therefore, the energy shift is small. It's almost negligible. So in O2 and F2 MO diagram, they keep this pattern of energy levels. All right. So again, when you look at these two PZ orbitals, they interact and form two MOs. One is sigma G, one is sigma U star. When you interact 2px and 2px, you get pi. 2py and 2py, you get pi and pi star. Okay, and over here you have 2 sigma G and 2 sigma U made from the s orbitals. Okay, now I want you to focus on this orbital and this orbital. Okay, these two may interact with each other. The interaction will always bump the higher energy MO up. It will bump this energy level down. It's just in O2 and F2. The energy shift is so small. Okay, you can't even, see that. But in B2, C2, N2, this is bumped here to here. All right, so it lies above the 1 pi u orbitals. And this one will be shifted down, maybe somewhere here. Okay, but that does not change the order between these MOs. So just down here. Okay, this one will be up here. Let's get back to the documents. I want to let you know this is not only true for B2, C2, N2, O2, and F2. You will observe similar phenomena in the third row elements. The sp mixing is more significant in aluminum 2, silicon 2 than in sulfur 2 and chlorine 2. All right, so unfortunately, I can only make a qualitative prediction here. So my prediction is this: in aluminum 2, you will see this 3 sigma G lies above the pi u orbitals. Okay, maybe we should call that 4 sigma G or even 5 sigma G because we're talking about aluminum. So you have like 3s interaction and 3pz interaction. So my point is this sigma G, the valence sigma G, will be bumped up to above the pi u orbital. You are not going to see that in chlorine 2. You are not going to see that in chlorine 2. All right? So what about transition metals? What about d orbitals? We're talking about sp mixing. Will d orbitals mix with p orbitals or even s orbitals? It is possible, as long as the symmetry is right along the bonding axis. But this is not in the scope of inorganic chemistry. I think you need to take quantum chemistry and also transition metal chemistry to better understand the sp mixing, and then you will see pd mixing, sd mixing, whatever mixing, as long as the symmetry is right. There's one more condition. I want to emphasize the second condition, other than the symmetry is right. The second condition is the overlap between the two interacting orbitals must be significant. So if the symmetry is not right, if the symmetry is not right, for example, if you have a s orbital interacting with a p orbital, and the p orbital is perpendicular to the bonding axis, then the symmetry is not right. The s orbital is symmetric when we rotate it about the bonding axis. The p orbital is anti-symmetric when we rotate it 180 degrees about the bonding axis. So in that case, the symmetry does not match. There's no interaction at all. You are not going to shift any of these two orbitals.